Okay, so we are on to sequences and series. A sequence is a function whose domain is the set of positive integers, and a sequence is symbolized by this bracket a sub n close bracket. The subscript n is always understood to start with 1 and to include all of the positive integers. You can think of those n values as the x values in an xy table and the sequence as a set of y values. So you could, down here in this first arithmetic sequence, you could think of this as an xy table where when x is 1, y is 3, when x is 2, y is 8, when x is 3, y is 13. I'm over-explaining it right now, more than I did in class, but I feel like I have the time to do that. All we're looking at right here is just the y column, and this is a sub 1, a sub 2, a sub 3, a sub 4, a sub n. So with that in mind, you can see the correlation between what you're used to seeing and what you're going to be seeing now. In pre-cal, you learned that the nth term of an arithmetic sequence is a sub n equals a plus n minus 1 times d, and a is the first term, and n minus 1 is the previous term number times the difference between the terms. So in this particular case, d would be 5 and a would be 3. However, arithmetic sequences aren't very interesting, so although they're great when it comes to linear functions, there's not much in real life that's linear. So moving on to geometric sequences. Geometric sequences are pretty common. They occur with simple interest. And you see here a geometric sequence with a common ratio of -3. The nth term of a geometric sequence is a sub n equals a times r to the n minus 1. That a, again, is the initial term, and the r is the common ratio. N is the term number, and a sub n is the actual term we're looking at. Some sequences are neither arithmetic nor geometric. You see examples below. If a sequence, that is the list of numbers, has a finite limit as n approaches infinity, we say that it converges to that limit. And if a sequence does not have a finite limit as n approaches infinity, then we say that that sequence diverges. A sequence might diverge because the limits are increasing without bound, or because the terms are decreasing without bound, or because there actually is no limit. Sometimes they just bounce back and forth a lot. You'll see examples of this in a second. In the first example, your values are just getting smaller and smaller and smaller, so it does converge to 0. That's fairly obvious. In the second one, although they bounce back and forth from the positive to the negative, they are still getting closer and closer to 0. And on the third one, they are getting smaller and smaller and smaller, and it also converges to 0. So we can We can hypothesize from that if the absolute value of r is less than 1, then the geometric sequence converges to 0. A series is a completely different thing. If I said series before, I'm so sorry. I mean sequence. Oops. On the other hand, in example D, you see that the numerator just keeps getting considerably larger than the denominator, which tells us that the limit as n approaches infinity of 5/3 to the nth equals infinity, so we can say that the geometric series diverges. So on example E, you can see that sign, it wavers between -1 and 1, so that diverges. That sequence will diverge. The limit as n approaches infinity of f, however, will be 3/5, keeping in mind n behavior. And it's same over same, coefficients you name. And then in G, it's bouncing between 2 and 4. If n is an even exponent, it's going to be 4. If n is negative, if the term is, not negative, odd, then it'll be 2. So that diverges. So it bounces between 2 and 4. And then in H, we apply L'Hopital's rule, and we see that it converges to 0. And on I, there were a lot of questions in class over this, so I tried to write out that factorial expansion a little bit clearer here for you. And you can see that it converges to 0 once we've written out our factorial in a way that we can see exactly how it cancels. Let me know if you have questions, especially on I. I'm pretty sure that previous classes are skipping over factorials, so if you don't understand factorials, I can go over those sometime. Nobody else has seen this page, so take it and run. In previous years, students were familiar with this formula, and they knew that geometric series converged to the sum of the initial term over 1 minus the ratio. I don't think you guys remember that. You may have seen it, but I think that it's not in your memory bank. Luckily, however, it's not that difficult to remember, and we can write out our series. A series is the addition or the sum of the sequence. A series is the sum of the sequence. So we're going to see this particular series written out as a sum. So as you can see, I rewrote it as a sum, and then I wrote the general term. I wrote the general term right here. This general term helps me identify exactly what R is, and R is the part that is actually taken to the exponent, and it helps me identify, or you identify, what the initial term is. And once you've rewritten it like this, it becomes easy to pop it into the formula. You can see here that your common ratio is 1/2. 1/2 is less than 1. Therefore, this series converges by the geometric series test. Those words are all important. You will need to be able to show what R is, and you will need to state this series converges by the geometric series test, or whatever test you are using. The example B, however, has a common ratio of 3/2, which is bigger than 1. Therefore, this series diverges by the geometric series test. You will need to be able to state that in words that clearly. And if you really need to, you can figure out the sum of the series using the formula that was highlighted above. And you can find that this particular geometric series, the sum of this particular geometric series is 243 halves. There's a piece in here that's way more important than it appears. It's this piece right here. If the limit doesn't equal 0, it doesn't tell us anything. If the limit equals 0, then it doesn't tell us anything. The nth term test for divergence only tells us if something diverges. It does not tell us if something converges. So we see that the limit of the terms is 2/3, which is not 0. Therefore, the series diverges by the nth term test for divergence. Because no matter what you do, that series, when you sum it, is not getting closer and closer to something. It just keeps growing and growing and growing. So in both of these cases, the individual terms of the individual sequences converge to a limit other than 0. Therefore, the series both diverge by the nth term test for divergence. In this last example, you see a series that converges by the telescoping series test. And you can see that all of the terms are going to cancel except for that very first term, which is 1/3. And we can say that that series converges to 1/3 by the telescoping series test. And thus concludes the math portion of this video. Now you can see my pretty little kitty. Her name is Nancy Drew, asleep on the back of my couch.